Hello. In this video lesson, I'm going to be going over how to use the magnetic field right-hand rule in a little bit more depth so that you can predict the orientation of a magnetic field from not only a straight current carrying wire, but also for a solenoid, which has that north and south pole as well. So let's go ahead and dive in. So just to review, anytime we have a current, an electrical current, these moving charged particles, we have a magnetic field that's being generated from that. And magnetic field lines always form closed loops, okay? So in order to figure out what that loop looks like and which way it's directed, whether it's like clockwise or counterclockwise or whatever, we use the right-hand rule. In the right-hand rule, your thumb always represents the direction of current. Your fingers represent the direction of the magnetic field lines. So if I have a straight current carrying wire like is shown here, and the current is going upward, I would point my thumb up and see the way that my fingers are curling around. So then that way I can figure out which way those magnetic field lines are looping around my current. Okay. Now, one thing that's challenging about talking about magnetic fields is that we inherently have to think in 3 dimensions because we have our current going one way and that's perpendicular to the plane that the magnetic field lines are in. So we're inherently covering X, Y, and Z dimensions. And that's tricky when we're trying to communicate in a 2-dimensional screen or on a 2-dimensional piece of paper. So to help us out, we've got some notation. So right and left, up and down, those are straightforward. We know how to represent those on a 2-dimensional piece of paper. We've got arrows to the right, left, up, or down. But then we also have that perpendicular direction as well, that if we have this flat surface, there's up, down, right, left, but we also have the direction coming out of the surface or going into the surface that we need to be able to represent as well. And so for that, we have an X and a dot. So if we're describing the direction of something that is going essentially into our surface, going away from you and towards the surface, that's represented by an X. If we want to represent the direction of coming out of that surface, so thinking about something coming out of your screen towards you or out of your piece of paper towards you, we would use a dot. The way that I think about that is I think of the directions as being represented by an arrow, like bow and arrow. And I imagine, if the arrow is moving away from you, you would see the fletching on the side, the little feathers, that might look kind of like an X, whereas if there's an arrow flying towards you, I hope there isn't, but if there is, you would just see the little point of that arrow right there. So another way to kind of think about those directions. Okay, so with these 6 different symbols, we can represent then all of those different possible dimensions in the X, Y, and Z direction. Okay. So let's just check in on our understanding of this right-hand rule then. So imagine that there is a wire that is coming straight out of your screen and right towards you, okay? And there's this current running across or along the wire that is from your screen towards your face, all right? So first question is, how would we represent the direction of that current in a drawing, in a 2-dimensional drawing? Okay, so if we want to represent the direction of coming out of the screen toward you, that's going to be represented by a dot. Again, think of an arrow getting shot towards you and you seeing just the tip, the little point of that arrow. Okay, so with that being the case, we've got this current that's pointing out of your screen towards your face. Second question, using that right-hand rule, what is going to be the direction of the magnetic field that that current is producing? Okay, so to do this, we got to use our right hand, right? So again, current is represented by your thumb. So you take your thumb and you point it coming out of your screen. So something kind of like this. So it's coming out of your screen towards you. And if you do that, what you're going to see is that your fingers are wrapping around counterclockwise. Okay, so my expectation then is that our magnetic field will form these loops, these circles that are going counterclockwise around our current. And we've been over this last one, but I just want to hit it again now that we have this different way of looking at this magnetic field. Does this magnetic field have a north pole? If it does, where is it located? If it doesn't, why doesn't it? So for a straight current carrying wire, there is no north pole and no south pole because there's not a clear location where our field lines are exiting or emanating out from. There's no clear point of origin. There's no place where they're going back in. They're just going around in a loop over and over and over again. Okay, so as a reminder, straight current carrying wires do not have north and south poles. But if we take that straight current carrying wire and we twist it into several loops and form a solenoid, then those loops will all kind of roll up around each other and we'll get something that does have a north pole and a south pole. All right. Now, as it turns out, we can apply this right-hand rule to be able to predict what the magnetic field of a solenoid will look like and predict where its poles will be on the basis of how the current is flowing through that solenoid. It's a little bit trickier, but here's the method that I've used that seems to work out pretty well, okay? So the first thing you're gonna do is choose a point on the outer edge of the solenoid, okay? So if this is, here's my little COVID era solenoid right here using a container of sanitizing wipes. Good times. All right. So if I've got my solenoid like this, choose a spot along the bottom or a spot along the top here. Okay. Someplace where the current is either going away from you or coming towards you. Okay. Choose one of those spots. Don't choose up here. Don't choose over here. Like, it's going to be too tricky. Choose along the outer edge. One of those spots. Okay. And then figure out whether your current is going into your piece of paper or into your screen or out of your page or your screen at that location. It's going to have to be one or the other if you're choosing a spot on the outer edges. So it's got to be either into or out of the page. Okay. So once you do that, once you know which way the current is going at that one location on the outer edge of the solenoid, you can use the right-hand rule just to figure out the magnetic field from that one location. Okay. And then you know that's going to be the same as the magnetic field next to it, next to it, next to it, all along that entire side of your solenoid. And so then you can fill that in, and then you'll be able to see where the field lines are exiting the solenoid and where the field lines are entering the solenoid. I realize that's still probably a little like, woo, hand wavy for you. So let's walk through an example together. Okay. So let's consider this solenoid right here. Where the current is entering in on the left, so the current is flowing down on the left, and that wire wraps behind the solenoid and then comes up in front, down behind, up in front, down behind, up in front, and so on and so forth, and then exits out upward on the right side of our solenoid. Okay? So the first thing I'm going to do, this is too overwhelming. There's too many things. It's going around and around and around. I'm going to choose one point on the outer edge of the solenoid. Okay, I'm going to choose this point right here, right where it after it's done coming down behind the solenoid and starts coming back out again. I'm just going to focus on that one spot for now. So if the current is going down behind the solenoid here, okay, if it's going down this way, goes behind it, then my current has to be pointing out of the screen at that location. All right, so current is going out of the screen at the bottom of the solenoid. So I would take my thumb and have it point out of the screen right there and then wrap my fingers around. And what I see is that at that location then, I'm going to have my fingers curling around counterclockwise, just as we saw before in that previous example. All right, so the magnetic field from that one little location on the wire is counterclockwise. Same thing is true for the location right next to it, and right next to it, and right next to it. All those little locations, all those little bits of wire along the bottom of the solenoid are all going to have that same counterclockwise magnetic field because all of them have the current coming out of the screen towards you at that location. Okay, so then that means that this whole side of the solenoid, all along the bottom there, my magnetic field lines are going counterclockwise. Okay, now that would be enough to be able to identify the North and South Pole. But just to kind of clarify this a little bit more and really, you know, do it all the way. All right. So again, we've chosen that point at the bottom. But say, for example, instead you chose a point at the top of the solenoid. Okay, instead of along the bottom edge. So I can follow the current then. It comes out on the bottom, goes up in front, which means that then at the top of the solenoid, the current is moving away from you into the screen. Okay, so if I choose a point at the top, the current is going into the screen. All right, and so if I then use my right hand rule for that, okay, so now it's going into the screen. So I take my thumb and I point it going into that screen, and I wrap my fingers around. I see that my fingers have to wrap clockwise. Okay, so you can do the same thing. Just take your thumb, point it up to against the screen, and you'll see that your fingers are also rotating clockwise as a result. Okay, so from this, regardless of which side of the solenoid you choose, we see the same pattern on both sides of our magnetic field lines are going into our solenoid on the right, and they are exiting the solenoid on the left, which means that the left side has to be the North Pole because that's where our field lines are emanating out of, and then the right side has to be the South Pole. Right? I know that can be kind of tricky, but that's the basic idea of how we can use that simple right-hand rule, whether we're talking about a straight wire or whether we're talking about a solenoid. Same thing either way. All right? Thank you so much. Let me know what questions you have. I am here to support you. All right?